Hi guys, it's going to be a video lecture for work and energy, and let's get started with the definition of work and energy. Alright, work that we know in our daily life is a little bit different than the definition of work in physics, because you might say it did a lot of work, but that's not what it really means in physics. To be able to do work, you are actually going to apply some force, and when you apply that force, object has to move. But it's not even enough. It has to move in the same direction of the force applied. All right, that's the definition of work in physics. And how do we describe that in like with the variables? Work is shown with capital W. You're going to apply some force and it's going to have some displacement. But how do we mathematically say that the force and that displacement are in the same direction? Then we use the term cosine theta. And here theta is also described, and this theta is the angle in between the force and the displacement. Alright, so in that case, if you look at the example, the object is basically displacing in that direction, which is to the right, and the force that we apply is basically in that direction. So what is the angle in between them? Theta. So as you can see, the displacement and the force vectors, they are not in the same direction. So in that case, then that means the force that we have is not going to do all of the work, or it's not going to be able to, all of the force is not going to be doing the work. So which work or which force will do the work? The one that is going along with the displacement. So how do you find that force that is going along with the displacement? In math, we use cosine because cosine describes the parallel uh, component of the angle. But what is happening to this y component? So this is basically f sine theta. Basically, this is doing no work because the displacement is going in that direction, but the force that you apply in this direction, so those two vectors have nothing in common. So this force is basically doing no work because no displacement is happening in the direction of the force applied. Alright, so that's why we are basically using force, displacement, and cosine theta to calculate the work. And if direction of movement and direction of applied force are perpendicular, like we had in here, then no work is done. Alright, what's energy? Because work and energy used together most of the time. Energy is basically ability to do work. So if you have energy, then you're going to be able to do work. Or if you would like to do work, you need to have some energy. And the SI unit for work is joule, and it's shown by capital J. And it's a scalar quantity. That means direction is not important. And work is also a scalar quantity. And however, we have positive and negative work and positive and negative energy. Then what is the meaning of that positive and negative if it doesn't indicate the direction? Negative energy or negative work is going to basically represent the energy that we lose, or that is the energy that is leaving from the system. And positive is meaning that you are gaining some energy. All right, or once you do positive work, then the object is gained energy. And sign of the work in that case, similar thing, work is a scalar quantity. However, that means direction is not important. But what is the meaning of positive and negative work? So if the work is positive, then that means displacement and the force, they are in the same direction. So for example, this guy is applying the force and the object is basically moving forward, so displacement and the force, they're in the same direction. So that means object is going to actually gain some energy, and the work that we do in the object is positive. But let's say in the same system we also have friction. So we are applying some force, F1, and F friction is going basically left. So F1 is getting the object move forward, so displacement is right. However, the force of friction is left. So the angle, if you also think about the angle version, the angle in between those two vectors is basically 180. And cosine 180 is -1. Or if you think about mathematically, if two forces are going in the same direction, the angle in between those two vector is 0 and cosine 0 is 1. So when two vectors are parallel, going in the same direction, maximum work is done. When they are basically going against each other, then the minimum work is done mathematically. I mean, not the minimum. The work is going to be basically having the negative value. So in this case, friction will do negative work, and the force that is applied is going to have positive work. And if you would like to have an answer, so let's say this guy is basically holding the weight, and how much work is he doing? So considering the fact that work is force and displacement, since he's basically holding it, there is no displacement, so this guy is basically doing 0 work. And soccer player is sliding on his knee, so he's basically moving in this direction, so this is the direction of delta x. But the force that is acting on him is basically friction, which is going against uh, his movement. So friction and displacement, they are going in the opposite direction. So basically the work that we have is going to have a negative sign. And the third case, this guy is basically applying the force upward, but the displacement is forward. So the angle in between them is 90 degrees. So the force that he applies is basically keeping uh, the food basically falling down, but it's not the reason that it's able to actually move forward. So the force that he applies actually do no work. So there's nothing that is done in those two cases. And when rock is falling, so the displacement of the rock is basically in the direction, and the force that is getting the rock fall is gravity, which is also going in the same direction. So in that case, the work that we have will be basically positive. You can see the descriptions. All right, forms of energy. So energy is not just one form. You have probably heard those two, but all of the others are also forms of energies. But those two is going to have a special importance. So you guys need to remember what are those and what are the others, because those two will have a special name, but the others are going to have different name. All right, so what is that kinetic energy? Is basically the energy of movement, and since it's energy, it's joules, it's measured in joules, and it's scalar quantity. But how do we calculate the kinetic energy? It's 1/2 mv squared. So you just multiply the mass and the square of the velocity of the object, and that's how you calculate the kinetic energy. And potential energy is basically stored energy, and it basically depends on two things. You can have gravitational or elastic potential energy. And gravitational potential energy is about how much energy you gained due to your height. All right, only one thing. Height is basically going to give you some potential energy, gravitational potential energy, regardless of your motion. All right, you might be at rest, you might be moving. It is not about having kinetic energy or not having any kinetic energy. It's all about the height. As high as you go, well, as high as you go, you basically have more and more potential energy. And actually, if you also think about the other version, you have more potential to do the wrong thing. So anyways, the height will determine your gravitational potential energy, and a way for us to calculate it is mgh. And potential energy sometimes is shown with capital U as well. And the other form of potential energy that we have is elastic, because it's also able to store some energy. And elastic potential energy is going to be created when you compress or stretch anything that is compressible and stretchable. And in that case, your potential energy will be similar, equation-wise, similar to kinetic energy. It's 1/2 kx squared. So k is your spring constant or force constant, and x is distance that you compress or, not end, or stretch. So you can compress or stretch. In both cases, you are basically going to create or store some energy, and that energy that we store is called elastic potential energy. And work energy, kinetic energy theorem. So the net work, there is also a relationship in between work and kinetic energy. The net work is equal to change in kinetic energy. So if something is moving with a constant velocity, then that means there's no change in kinetic energy. So that means there is no net work. All right, this is an important thing. It doesn't mean that there is no work, but that means there is no net work done in the system. And power is another quantity that we need to know. Power is doing some work. Yes, it's important, but power will include the time of that, like the effect of time and that quantity. So how much work you do in given time will determine how much power you have. And it's a scalar quantity, so there's no positive or negative, or there's no direction for power. And watts is basically the unit of power. And once you basically reconsider that work and time, work can be written as force times distance, and distance over time can be written as speed. So you have basically a couple of different formats or forms of power. It's work over time, force times distance over time, or force times velocity or speed will also give you the power. All right, conservation of energy. So conservation of energy states that energy in the world or in the system is constant. So that means we cannot create or destroy the energy. But what can we do with the energy? We can basically convert it from one form to another. It's just like the currency. So the total number of money that we have in the system is the same, uh, the value-wise. But once you basically convert, so you can convert from one currency to another, but it's not going to basically change the amount of money that you have. It doesn't matter if you have, let's say, $10,000 or 900 euros. They are basically the equal amount, but the form is basically different, and you can convert from euros to dollars and etc. All right, so remember I said kinetic and potential energy, they're going to have a special name. So they are basically called mechanical energy. So especially the kinetic and potential energy, when you add those two together, then we call that mechanical energy. And why is it important? Because those two forms of energy is also going to be conserved. So we said total energy in a system is conserved, right? So, but energy also is divided into two as mechanical. And what is mechanical? The kinetic and potential that we have. And all of the others are going to be called non-mechanical. I feel sorry for the non-mechanical energies because they considered as others, right? Anyway, so mechanical energy is kinetic plus potential energy, and all of the others are called non-mechanical energy. But again, why is this mechanical energy is important? Because it is also conserved. So the sum of this kinetic and potential, and two forms of the potential, is going to be constant in a system. But when is it going to be constant? If we don't have others in the system. And let's remember what is others. So sound energy, chemical, electrical, light, heat, thermal, and in this case, this is going to be the rule breaker for daily life, because thermal and heat energy is basically created by friction, or sound is also. So most of the systems, when they are basically happening, or like any motion, they're basically creating some sound. So that energy is lost. So and heat and thermal energy, again, when you have a friction, they are lost from the system. You cannot get them back. All right, so that's why for you to be able to conserve kinetic and potential energy, you should not have any non-mechanical energy in this system. All right, so, and what is conservation mechanical energy stating? Initial mechanical energy is equal to final mechanical energy. So let's assume that we are in space and we just drop things and there's no air resistance or anything. So what's going to happen? You basically drop the object. So once it's basically in the air, when time is 0, it's basically 1 meter height. So it's at rest. So it's going to have basically 0.74 joules of potential energy, and that energy is again due to height. It doesn't have to move, or it doesn't have to be at rest. It's due to the height. And then since it's at rest, its kinetic energy is 0. But once we are considering the total mechanical energy, it's 0.74. And once it's dropped, what's going to happen? It's going to fall down. So its height is going to decrease. But as it decreases, what's going to happen? We said the mechanical energy is going to be conserved. So height is decreasing, so your potential energy is decreasing. But what is the other energy that we have in the system? Kinetic energy. So potential energy will decrease, but kinetic energy will increase with the same rate to be able to basically compensate the energy difference. So this guy will speed up, and then potential energy will be decreasing, but the kinetic energy will be increasing, but the end, like the total energy that we have in the system, will stay the same. So we are not able to see the mechanical energy in this diagram, but mechanical energy is going to be something like this. So your mechanical energy is the same throughout. But what is happening? So one energy is basically decreasing, the other energy is increasing. And that increase and decrease, it's not linear, it's basically curved. So energy conservations are going to basically have such a diagram or graph. All right, so what is next? All right, so other way of basically solving questions about conservation of energy is this diagram. So this diagram can help you to set your question or your variables neatly. So initial energy and final energy. So what are the forms of energies that we have? Kinetic, gravitation potential, and spring. So initial and final, basically, that's the total energy. But there's an extra thing. If there's an extra force in the system, that means that some extra work will be done. So that is basically added in the system, and if you have extra work in the system, your equation is not really changing. So this extra work, however, should be included in your calculations. All right, so that is just a way to set up the forms of energies that you have in the system and before and after, and if there's any extra force that you have in your system. All right, so that is it for work and energy. See you in the next videos.